Hello, everyone. My name is Jinghui Qin. So today's topic is accelerated data frame with Dask-cuDF on multiple GPUs. The reason for considering this topic is because of a user that I helped recently. The user was from mechatronic engineering and worked on a machine learning project using XGBoost. XGBoost is a leading machine learning library that provides optimized gradient boosting framework for supervised machine learning. He started with a CPU-based solution. Since his dataset was large, I initially helped him with using Dask on our cluster, in specific to scale up his training workload with Dask across multiple nodes using CPUs. After he learned that NVIDIA Rapids was available for working with Python on GPUs, he submitted a ticket again and asked about using Rapids with GPUs on the clusters for his work. Then he was able to accelerate his code execution on a GPU. But initially, he could only train on a reduced dataset on a single GPU, which was only about 30% of his original dataset because of the limited device memory on a single GPU. Since Dask-cuDF integration allows scaling out a workload across multiple GPUs, eventually he was able to process the entire dataset across multiple GPUs. In specific, he successfully ran his XGBoost code using a Rapids container on a full GPU node on Narble that has 4 800 GPUs. Each GPU has 40 gigabytes of device memory. It was exciting to see the significant performance improvement on GPUs. I think that's nice and encouraging. The main component he used were cuDF, cuML, and their integration with the Dask-cuDF. Those were all included in the NVIDIA Rapids suite. Rapid includes many data science tools in Python for working on GPUs. So for today's webinar, instead of introducing cuML for machine learning on GPU, I would like to introduce a more basic and general component, cuDF, and its integration with Dask as Dask-cuDF for accelerated data frame operations on single and multiple GPUs. Okay, I will start with an overview with some background, and then I will switch to a demo on the cluster with some examples. The demo examples were originally from NVIDIA workshop. I have ported them into Jupyter notebooks that can run on our cluster to work with a Rapids container. I hope it can be helpful if you are considering to accelerate your analytics workload in Python using GPUs on the cluster when dealing with large data and heavy computations in Python. You will see that after making a minor change in the Python code, significant speed up can be achieved on GPUs. As we know that data science is a field about extracting knowledge and get insights from data. For example, using a machine learning technique to learn and get insights from data for making some decision or prediction for future. Okay. To work in the data analytics field, Python is one of the most widely used programming languages because it is easy to learn and to use. It's open source and has many free available Python libraries and frameworks. For example, NumPy, SciPy, Pandas, and scikit-learn, and etc. They are commonly used Python packages in data science. NumPy is a base and dimensional array package for numerical computing with Python. SciPy extends NumPy with a collection of mathematical functions and the libraries that were compiled from C or C++ or Fortran and wrapped up with a Python interface. And the Pandas is a Python library with some easy to use data structures and the tools, especially for dealing with tabular data. And the DataFrame is the most commonly used object in Pandas. You can think of it like a spreadsheet or a table from a relational database. Okay. And the scikit-learn provides tools for data mining and machine learning. It also has tools for data pre-processing, some feature study, and the tools for building models in machine learning, and etc. Okay, these packages provide consistent API in Python. They're easy to learn and use, and they work fine when dealing with the data that can fit into the memory on a single server or a single computer. Okay. But the challenge is how to process lots of data, a very large data set. For example, the size of the data set is larger than the memory size on a single computer. To process a large data set, the one approach is through a distributed data analysis with scalable computing supported. In order to do a distributed data analysis, it requires to have a platform with advanced computing resources, such as a cluster of many machines, like the picture showing here. And also have some software framework that can be deployed to such a cluster and support the distribution and the execution of the workload on such a cluster. So Dask and Apache Spark both can provide such a framework for distributed data analysis. So Dask helps dealing with a large data set from two aspects. At high level, Dask provides a task graph-based framework to partition large data collections into smaller chunks, and the parallel algorithm or implemented for processing those tasks in parallel, and provided with familiar APIs that are similar to those in NumPy, Pandas, and the scikit-learn. At low level, Dask provides a dynamic scheduler to distribute those tasks and have them executed in parallel, either using multiple cores on a single computer or using multiple machines on a cluster. Apache Spark provides a similar framework in supporting distributed data analysis. In addition to supporting Python workload, it also supports workload in Scala, R, and Java. Another approach when dealing with large data and heavy computation is to make use of GPU accelerators. Here, GPU stands for Graphics Processing Unit. It is a specialized processing unit initially designed for accelerating graphics output on a display device. General purpose GPUs have been used for scientific and engineering computing because GPUs are highly parallel structure makes them more efficient than CPUs, especially when dealing with large blocks of data in parallel. For working with GPUs in Python, deep learning is one of the areas in machine learning and AI field that involves intensive computations. Some widely used deep learning framework in Python, such as PyTorch, TensorFlow, they all support distributed execution on a CPU cluster and also on a GPU cluster for either data parallel or task parallel to accelerate the execution when dealing with large data and heavy computations. They were provided with the user-friendly Python interface for working on GPUs, but they are only for using within those deep learning framework. For data analytics with Python in general, it would be nice if we have some Python libraries available with APIs that are similar to what we're familiar with when working on CPUs. For example, those in NumPy, Pandas, scikit-learn, but can move the workload onto GPUs to accelerate the execution. For example, for those workloads in loading data, extracting data, transforming data, filtering data in a general analytics workflow, but dealing with a larger amount of data. So here comes Rapid. Okay, so what is Rapid then? Rapid is a suite of open source software library from NVIDIA. It is mainly for executing data science and analytics pipelines on GPUs. It relies on NVIDIA CUDA primitive for low-level compute optimizations. It is also scalable and can be scaled up across multiple GPUs after their integration with Dask. It also provides user with a friendly Python interface. For example, GPU-DF is a Python GPU DataFrame library for manipulating data, such as operations in loading data, joining data, aggregating data, filtering data on GPU, and provided with a Pandas-like API. So we will use it in our demo example, okay? And the cuML is a GPU accelerated machine learning library with some machine learning algorithm and some mathematical primitive functions implemented for execution on GPUs and provided with a scikit-learn-like API, okay? And the cuGraph is for graph analysis on GPU with functionality similar as the CPU-based library, NetworkX, which is for graph theory analysis and social network analysis, okay? cuSignal is for GPU accelerated signal processing with a collection of libraries such as cuPy, NumPy, to speed up NumPy and SciPy on GPU, okay? In our demo example, you will also see a drop-in replacement of NumPy with cuPy when working on GPUs, okay? cuSpatial is for geographical analysis on GPU, specific for geospatial data analysis on GPU. And there are more. And with all these libraries from Rapid, it was claimed that you can execute end-to-end data science and analytics pipeline entirely on GPUs with minimal code changes, okay? So that's exciting. So here are some helpful links for the API documentation and some examples and use cases and the blocks for using Rapids, okay? Okay, back to here. For Dask-cuDF, here are the main components involved in using Dask-cuDF. So Pandas, as has been mentioned, is a CPU-based DataFrame libraries for dealing with tabular data. And the cuDF is a GPU-based DataFrame library and provided with a Pandas-like Python interface. Okay, as we mentioned, when dealing with a large data set, Dask provides a framework for scalable computing. It is achieved through a Dask cluster deployment, which consists of one centralized Dask scheduler and one or more Dask workers. So here, Dask scheduler and the Dask workers are processes running at backend, like daemon processes. They can be deployed on a same machine to work as a local Dask cluster and handle task execution in parallel using available cores on the machine. The Dask worker can also be deployed on different machines and register with the Dask scheduler to handle the distributed task execution on a cluster. Okay, now we introduce the Dask-cuDF. It is for scaling out data frame workload in cuDF data frame partitions across multiple GPUs. It is achieved through the Dask-cuDA integration. Okay, similarly, a Dask-cuDA cluster consists of one Dask scheduler and one or more Dask-cuDA workers. and each Dask-cuDF worker communicates with the task scheduler and takes care of the task execution on a specific GPU. Okay, to deliver the cuDF workload to a Dask-cuDF cluster, a client instance needs to be created and connect to the Dask-cuDF cluster. Then the operations on those cuDF data frame partitions are sent to the task scheduler and distributed to those workers and processed on each of the GPUs. Okay. All these are handled at backend for you. Okay. So in summary here, Dask is a flexible library that makes scaling out a workload simple. Okay, Dask allows the Pandas data frame partitions to be executed in parallel on a CPU cluster, and the Dask-cuDF extends Dask to allow cuDF data frame partition to be executed across multiple GPUs. Okay. So we will see more details in the demo example shortly. So all these components are included in the Rapids container, in the Rapids suite, okay. Here is a code block to show how to create a local CUDA cluster to work with a multiple GPU on a GPU node, okay, and how to create a client to connect to this cluster, okay. So yeah, so you from Dask-cuDF package import a local CUDA cluster, and also from distribute package import a client package. Okay, so by default, the traditional TCP protocol is used for the communications among those workers and the Dask scheduler. Since the communication can be a major bottleneck in a distributed computing, so Dask-cuDF supports integration with the UCX for accelerated networking communication. Okay, that supports a variety of transport methods. For example, NVLink or InfiniBand if they are available, or TCP for system without those. Okay, so this example showing here is to specify the protocol as UCX and also enable TCP over UCX, so which provides a better bandwidth through the communication bandwidth or throughput for the communication. This change doesn't need any special hardware as long as UCX Pi is installed, which is included in the Rapid suite. So this is just UCX Pi, just Python bindings for using UCX communication protocol. Okay. So during my test with the demo example, it actually performs better than the default TCP transport. Yeah, simply enable TCP over UCX. Okay. Yeah, depending on the network topology on a GPU node, here is another example to turn on all the other options for using NVLink and the InfiniBand. Okay, the transport here are not mutually exclusive, so you can use all of them together as long as you are sure that the relevant GPUs are connected with NVLink or InfiniBand adapters here. Okay. So there are also some parameters for specifying how many workers to create, which GPU to use. By default, the number of workers will be the same number of the accessible GPU devices you requested. Okay, so you can check this documentation here. There are a lot more options. Yeah, for how many worker, which worker you to use. Yeah, there are many options there. Okay. Okay. So how to use Rapids on our cluster? NVIDIA provides 3 options for rapid installation. The first is using Conda, since on our cluster, Conda is not recommended to be natively installed because of some management and performance concerns. So you cannot do Conda install on the cluster. The next option is build from source, but that's not a trivial task because it involves complex configuration and dependencies. And also considering Rapid is still in active development. Newer versions are released frequently. The maintenance will be challenging if installed natively, okay? To save the efforts in building from sources, NVIDIA provides Docker containers for each released version of Rapid. You can think of a Docker container as a standalone package that includes everything needed to run some applications. For each release, the Rapid version, NVIDIA provides Docker containers with different combinations of Python version, the CUDA library version, and also the Linux version. So that's very nice. On our clusters, Docker engine is not supported, so you cannot directly launch or start a Docker container. Instead, another types of container option is supported. That's a Singularity container, which has been renamed as Aptainer container for the recent versions. And you can build an Aptainer container based from a Docker container image. And that is the option currently supported for working with Rapids on our clusters, okay? So to learn more about using Aptainer on the cluster, you can check this Docs wiki page. And there's also Docs wiki page for Rapids. For example, if you want to find where to find a Rapids Docker container from NVIDIA and how to work with a Rapids container on the cluster. Yeah, I will also give a demo shortly to interactively with a Rapids container on a GPU node. One thing I would like to mention is that the size of a Rapids container is relatively large, about 5 gig to 10 gig, that large, okay. Building such a container image requires large resources and takes a long time. It could take around 30 minutes to 1 hour to complete. So if you need any help to build a Rapids container with a specific combination, you can send us a ticket. So then we can help you build such a container image. So for the demo example, we are going to perform a simple and also very typical task in data analytics, applying a user-defined function for some data transformation. So we will compare 3 use cases. The case 1 is a general CPU-based solution, applying a user-defined function on data frame columns using NumPy and Pandas. Case 2 is a GPU-based solution with CuDF and CuPy. So CuPy here can be considered as a drop-in replacement for NumPy and the SciPy on GPUs. We will compare the changes in the Python code and their execution performance on GPU. Both case 1, case 2 will use the same data set, and it fits the single GPU memory for the demo purpose. Okay, and then case 3, sorry, I wrote wrong here. So case 3 here is to work on GPUs, but the example data set is about 9 times larger and cannot fit in on a single GPU memory. Okay. the Dask-cuDF is used, we will create a local CUDA cluster on a full GPU node that has multiple GPUs and compare the changes in the Python code in using Dask-cuDF. Okay. Also, we will monitor the GPU usage on a GPU dashboard during the execution. So yeah, we will be using a rapid container that I built based on a Docker container from NVIDIA with these combinations. It's a rapid version 22.12. So it was released December last year. It's the most recent version. Okay. And work with the CUDA library 11.4 version and on Ubuntu 20.04 with Python 3.9. It's a runtime type of container that includes an option for interactively working with Jupyter notebooks. Okay, so you can check here. This is the NVIDIA GPU cloud. They maintain a repository for all the rapid container. As you can see, you have different combinations. Yeah, really depend on what your preference. You can build a obtainer container based from these. Oh, yeah. Oh, you see the even newer version for just released. That's the most recent one. Okay. Okay. Yeah, here is a table listing the GPU resource on each of the clusters that you can use. So here is the total number of GPU node on each of the cluster, and this is the number of GPUs on each GPU node on a cluster. Okay. As you can see here, there are multiple GPU types available on different clusters. The GPU memory size are also different for different types of GPUs. The most recent type, also the most powerful type here are those NVIDIA 800 types GPU on Novel. Okay. Beluga has a V100 types GPUs. When requesting a GPU on Beluga or Novel, you don't need to specify the type of the GPU because there's only one type of GPU on those clusters. And the CEDA and Gram has multiple types of GPUs. Yeah, with different device memories on different type of GPUs. And you can check this Docs wiki page to find out how to request a GPU for a specific type on each of the clusters. Okay, now we'll switch to a demo and working with Rapid container on a GPU node on Gram. I already request an interactive session on a GPU node. I will run some examples interactively through Jupyter notebooks with a Rapid container. Okay, now as you can see, I already have this compute node reserved for its interactive session on a GPU node. I request this through salloc command. Yeah, and you can check NVIDIA-SMI. See, as you can see on this node, I have two P100 GPUs. Okay. The device memory is 12 gig. Okay, so this is on Gram. Yeah, this is the compute node. Yeah, I'm working in my directory here. Okay. So the first thing to do here is to module list. As you can see, these are default list of module. We need to load obtainer module. Okay, oops. container module load, sorry. Okay, so load mod, then we will use check. Here are the container image that I have. I'll use a container shell to access the container shell. So with --nv option to bind my project and the container image, I will be using 12 CUDA Ubuntu. Okay. So now I'm in the container shell. Okay. Oh, probably I will, sorry. I would like to show the command again. So here, this command, so --nv option is for bind mount the CUDA drive on the host to the container. So you will be able to access the device from inside the container. The -b option is for bind mount any file system you would like to access from the inside the container. Okay, so obtainer shell is the command to access this container shell. So now let's check. First is to check if you are able to access the device here using NVIDIA-SMI. Yeah, it's good. So we are able to access device inside the container. Okay, the next thing to do is to activate the Rapids environment. So we need to initiate conda because conda is included here. Okay, this is just you see initiate conda, then you need to activate Rapids. Okay, yeah. After you see the prompt change to this, you are ready to work with Rapids package. So we can do conda list and grep Rapids. You will see. Yeah, here are the components included in this environment. As you can see, CUDF, yeah, cuGraph, cuML, everything you needed to work with Rapids. Okay. And it also include Jupyter. So we want to start Jupyter Lab here to work with browser. Yeah, with we'll launch this Jupyter server. So okay, so here is the URL that you will use to connect to this Jupyter server. So here. Okay, so but if I type this URL on my local browser, it says the site cannot reach because this Jupyter server is running on the compute node that has no internet connection. So we need to set up a tunnel so to forward this port to a local computer. Okay, so you open another terminal here to type this command. Okay, this will forward everything running on this compute node to a local port 999 through the login node that's on Gram. Okay. So for our staff member, we need to provide a second authentication code here. Okay, good. Yeah, after you set this way, then leave both terminal open. Let's go back to the terminal here. You need to modify this part because we already forward everything running on that port to a local port, local host with port 999. You can use any other port. Yeah, this way we are connect to the notebook server running on that compute node. Okay, here is my directory. As you see, I have a couple of notebook. This is the first notebook we would like to show here. Okay, you see, I have a data folder, and this I have a 3 data set. Okay, two available here. Okay, so the first notebook here is for doing, okay, this is a little bit larger. So we are going to do some great coordinate conversion on CPUs. The example data sets are simulated the census data originally based on some UK's population. I have split the data into three CSV file in different size. Yeah, just for the demo purpose. I will start with the small data set here. Okay, let's run this notebook. Select and all below. Okay, okay. As you can see, I just import the NumPy and the pandas. Okay, here the pandas read CSV file is for loading this data into the memory, the CPU on the host. Okay, so another feature for this notebook server, you see, it has this dashboard. You can observe the resource usage while you are running this notebook. Okay, it is finished. So the data loading took 12 seconds, or 27 seconds for running this on the single GPU, or on the single core on the CPU. Okay, this D types attribute can display the schema of this data frame. You can use the shape attribute to get the shape of this data frame is 40 million samples, 40 million rows with a 6 column. And the head function call give you the first 5 samples from the data frame. It has age, and the sex, and the county, and the latitude, longitude of the residence, and a person's last name. Okay, yeah, it's a very simple data frame. So the UDF function defined for grid converter here with NumPy is to perform coordinate conversion. So here is the function passing latitude, longitude, but it will return coordinates called the OSGB 30 coordinates. Yeah, they have some complex mathematical formula. Yeah, so if you would like to learn detail, there is a paper about this. So let's go here. So, okay. So this function define take 2 attribute, the latitude, longitude. It also accept the input as a radian, but default is for degree. Okay. And the return northern eastern coordinate in this some OSGB coordinate system. Okay, so it using NumPy with this implementation. You see NumPy math library. Okay, to apply this transform transformation on the data frame, you simply passing the column latitude, longitude of that data frame, and then assign the return to as additional column you appended to the data frame called the northern easting. It took 32 seconds to complete this operation. And here is the result data frame. Okay, you see we have 2 additional column. Yeah. You can also calculate the average of those 2 columns just for demo purpose. It took 1 second something. Yeah, get the average. Okay, the describe function call will get you stats information for those numerical columns in this data frame. It took 8 seconds something. Okay, so this is for the CPU performance for this data set. Okay, and it's very simple. So let's get back to here to get the second notebook. Okay, in this notebook, it's doing the same thing, but on a GPU. So yeah, before we run in this code, let's see what changed. Before we run this, what changed in this code? Just the import part. Instead of NumPy and Pandas, we import CuPy and the CuDF. You see here, read CSV function is exactly the interface is same as in Pandas, okay? And also, yeah, we will check this attribute, and then the function with CuPy, the UDF function with CuPy, the interface are the same. The only difference is you replace all the NumPy library part with CuPy. Okay, you see, that's the only changes. And also here we do the same calculation for the average of the additional 2 columns. As you can see, yeah, they are the same. So let's run this, run all the cells. And we can also monitor the GPU. It's done here. Okay. Is it finished? I guess it's finished already. So yeah, this is before we loading the data. As you can see, the GPU usage memory is it's 0. Okay, after, oh, it's just a 2 megabyte with some library imported there. So it took 12 seconds. It's, yeah, less half of a previous, yeah. And then here you see the data was loaded into this single GPU. And then you can also checking the GPU here. Oh, it's all finished. Hi. Same here, you can check the data type and the shape. And let's see. Using 1 second, previous it's 20 seconds something, right? Is that 20 seconds something? Oh, 32 seconds. You see, using a single GPU, it only took 1 second to complete this because everything is running on GPU. We don't even have time to monitor all. But the GPU memory, as you can see, all the data still located on the single GPU, just using 1 GPU. Okay, yeah. We also called the describe. It took 1 second. Previous, it's about 6 seconds. Is that? Oh, it's describe. Yeah, 8 seconds used. But this, you only took like less than 2 seconds for doing the same thing, but this is on single GPU. Okay, so that's nice. You see the performance improved. Simply change CuPy and the CuDF, yeah, import. So not big change in the Python code. But if we try to increase this, because I have 3 data set to the mid-size, okay. So the mid-size data here, let's kill this kernel to clean the GPU. I will clear all the output and then apply the kernel again. Okay, so I increase the dataset size to run this again. It was loaded. Oh, that's nice. Everything still work. Okay, but when we call this function, we had some error. It says out of memory, the CUDA error. That's really bad. Okay, so the data seems okay, sits here, but when we call this function, we simply call the CUPA library to do the calculation. So seems that there is not much you can do with the CUDA memory allocation or anything. So that's bad. So to resolve this problem, there are only like 2 options. Either you use a GPU with a larger memory. Yeah, but this one only have a 12 gigabyte of memory. If you run on a memory with a 16 gig memory for this data set, it will be okay, as I tried. Another option is to work with multiple GPU. And we have 2 GPUs here, right? So right now, we only use the 1 GPU. So now let's switch to the third notebook here. Yeah, I will kill this 2. Yeah, make sure the memory, GPU memory is clean. So this is using CUDF, Dask-cuDF, okay, multiple GPUs. As we mentioned in the slide, first thing you need to do is create a local CUDA cluster. Yeah, with this option, I will just put here for better performance. And then you create a client instance to connect to such a cluster. Make sure you have this cluster create first before you import this CUDF library, so they don't lock to a single GPU device, okay? And then we will also load here, we load the large data set. Large data set is 18 gigabyte with like 300 million samples. It's about the same size as the US population, okay? Then we use the same read CSV file function call to load the data. And we will check all the functions here, okay? So let's run and above here, okay. This is not, okay, it's gone now. Let me run all the cell and above. Yeah. So as you can see here, we have a client, then connect to this cluster. We can check the cluster information. Okay. It has 2 workers because this GPU node has 2 GPU, right? The scheduler information is the Dask scheduler, okay? It has 2 worker, and the communication protocol we're using UCX, okay? By default, it will be TCP if you didn't provide any options here, okay? So as you can see, each worker by default using a single thread. This is the host memory on that this worker can use, and the device memory is 12 gig. That's the P100 GPU. Yeah, another worker is here. Okay, we have 2 worker to takes care the workload on each of the 2 GPUs. And then we import this library. Here, as you can see, this data set is 18 gig, okay? So at the beginning here, we check the device usage. You can also check the memory here. Yeah, after we load the data here, you call this read CSV, okay? It only took 1 second, but the data loaded, you can check the status of the device again. You see, it has some data loaded, but seems not large enough to indicate that the entire 18 gigabyte of data being loaded into memory. Similar as working with Dask DataFrame on CPUs, a Dask-cuDF DataFrame is a delayed object, okay? So when you call this read CSV function, it simply breaks the data frame into smaller Dask-cuDF partitions and creates a computational graph. The actual operation of loading data are not performed yet. So that's why when you call this, D types can still give you the data type because we already provided here, right? And the shape didn't give you the total number of the cores, but just showing you the column didn't give you a number of samples because data is not loaded, but you still can check the first couple of samples. Okay. We can use the partition to see it automatically partitioned the data into 69 partitions. But if you want to do any calculations here, it returns right away without giving you the actual evaluation if we want to do average here. So similar as using Dask on CPUs, you need to call this compute explicitly. So let's run all the cell and below to check all the performance here. Yeah, why it's running. So you can see it starts working. So both GPUs are busy, right? For doing the calculation. This is the memory usage on GPU, the 2 GPU. You can see they're busy working there. So we'll let them running, but I will explain here how to define a UDF for using to do the grid conversion on Dask partition. Since the data frame is partitioned into cuDF partitions, so in this UDF function, this is the previous interface we defined on CUDA on single GPU. So here we need 3 changes. So rather than passing in the latitude, longitude, you need to passing in a data frame partition as one of the attributes and specify the column on that partition, okay? And then the rest is the same as before. Okay, that's the interface difference here, okay? You're passing the first attribute as a data frame partition, okay? And then here, as you can see, the latitude is this column convert into Cooper array type, and the same here. And then the rest of computation is exactly same as the previous single GPU version of that function. Yeah. But the return type here is different. Instead of return to Cooper array, we just convert the Cooper array into GPU series object and assign to additional column in that data frame partition. So after this function return, the data frame partition actually was modified with the 2 additional column appended. Then to apply on the entire data frame, you need to call this map partition function. Apply this map partition function with this function you defined. So this will apply to the data frame, Dask data frame partition. As you can see, it completes here already, only use 300 something millisecond. Okay. I know it's time's up. It's at one clock. That's just reserve that time, but we can still, hopefully, yeah, we can still take a look. Oh, it's not done the computation yet. But that's okay. So you see the difference, but we can check. I have, okay. It's not done yet. So, but the time you see the changes here, it's only 3 millisecond. Yeah. For those calculation here, you see each of them only took like 10 seconds something. That's for almost 10 times larger data set. Sorry. So, because yeah, I have I think it's the reservation. Yeah, reservation time. I should put a longer time for this. Yeah. So I think that's all you see for the demonstration here. Sorry for cutting off, but you see the performance of using, yeah, you get the result. Yeah, another thing to mention here is using Parquet format, okay? So maybe I can show some result from my previous, let me change to local. I have some data saved from previous. Okay. Yeah, this is the result. This is the result, the same thing I run before. So have the information saved on my local computer. So we can see the changes here. You see, that's exactly what I just ran on the same compute node with 2 P100 GPUs. The things I would like to show is using the Parquet format, okay? So you can save the data into disk as a Parquet format. Parquet format is more efficient to the Apache Arrow memory format for using Rapids. Parquet also will compress the output from about 18 gigabyte to the smaller size, as you can see. Yeah, save the data frame partitions. See, each partition will be saved into a single file. And then when you load the data into Dask-cuDF data frame, you can direct using read Parquet to load the Parquet. You just provide the directory. So it will using parallel IO to load all the Parquet data into a data frame for the calculation. So this part you see only 3 seconds, that including loading data and also calculate the average on the 2 additional column. And then you can also do the same thing as before. Okay, I think that's all for the demo here.